Get ready for fun on this video because we're going to talk about chemistry. Yes, we'll go back and talk about spin operators and all that algebra and Hilbert spaces, but let's realize what we're going to do is talk about not just one spin, like in hydrogen, but two. Count them, two spins. See how they're all nicely laid out there? And then we'll show why once you add one more spin, it won't fit. And you've got to go up to lithium, where you add another electron here. So hold on to your hats. We're going to dive into this with a fierce attitude. If these items, the little hat over it indicates a spin operator, the X indicates the X-axis, Y and Z. If these don't look familiar to you, you haven't watched the earlier videos. So I'm sorry if this confuses you. No, I'm not sorry. You just need to go back and watch the earlier ones. Anyway, these are operators, and they operate in a Hilbert space represented as a two-dimensional complex space. They aren't in a 2D complex space. They're in a Hilbert space. And that is where the state of these things lie, but it's not the same as a 2D complex space. That's why down here I say represented, and down here it says stands for the Hilbert space, for the spin, and then this symbol, rather than an equal sign of a 2D complex space, it's got a little squiggle over the top. Now at first you're going to think that's approximately equal to, but that symbol's a little different. It has two squiggles. So this equal sign with a squiggle over the top, it stands for the fancy word isomorphic, which basically means the 2D complex space represents the way the spin thing operates. And these old friends here, plus X, plus Y, plus Z, those are all the different axes that we can have the measured values. We can also have a minus Z, a minus Y, a minus X. So those are vectors in this Hilbert space. Maybe that makes some sense, maybe not. If not, again, the earlier videos pounded this into your head, hopefully. Now, this is the exciting part. This is where you get passionate. Two electrons. Two electrons. We're going to examine what happens with two electrons. They can occupy the same Hilbert space. Here's the total space. And it combines with the spin of one electron and the spin of the second electron. And this thing that looks funny here looks kind of like, I don't know what it looks like. It's a circle with a square inside of it, or an X, and that is not a regular multiply sign. It's kind of like a multiply sign, but it's a different kind of product. It's a tensor product. Whoa, what in the heck is a tensor? A tensor is kind of like a vector, because a vector is actually a version of a tensor, but a tensor product produces, look what happens. We go from 2 dimensions to 4 dimensions. Wow, if we couldn't draw a 2-dimensional complex space, then we sure as heck can't draw a 4-dimensional complex space. So your brain needs to just accept these things and keep going. Now for notation. And I made a little improvement up here. I showed the plus z minus z. These are the z measurement basis states, which you probably already know. And down here, because it's very difficult to draw a bold S on the board here, I'm just going to put a line over it. Every time I put a line over a letter, that means it's in bold. So a bold S indicates the spin operator, but it's a spin vector operator. It involves all three: S sub x, S on the y-axis, and spin on the z-axis. And if we square that value, we can get the vector operator magnitude just like we would with a regular vector. Now, to keep the notation simple, if I say S, when I use S, we're talking spin all the time. So when I put S sub x, I really mean S operator sub x. When I put plus in this notation, that indicates a up direction on the z, or aligned on the z axis. Everything's kind of focused on z. Over here, if we have an S total for, now we have 2 electrons rather than just 1. Now that's going to equal the S1 vector spin operator and the S2 spin operator for electron number 2. If we want to get the S total squared, then we have to do the vector thing here. Notice I'm adding the 2 vectors and then taking the dot product of those. Now, instead of putting total down every time when I'm talking about multiple electrons, I'm just going to put the S. So hopefully that gives us all the notation we need. Here's an interesting state vector, a big S and a big M. Now you can probably guess the S is for spin, but I bet you're not so good at guessing what the M is. This M value comes from angular momentum type notation, but let's just keep going and call it the spin space state vector. Doesn't that sound fancy? Aren't you smart to know that? Well, S is the spin, M is projection onto the axis. And to get us started to understanding this, let's take one electron. What's the electron spin state? Oh, it's 1/2, of course. And what is the M value that we're going to use? Well, we've got 2 choices. If we start here at the spin number and keep adding 1 to it until we get to the spin number. Did I say that right? The negative spin number, keep adding 1 till you get to the positive spin number. Okay, here's the spin, 1/2. We know that, or we should know that, or we might question it. But anyway, spin 1/2 for 1 electron. The first state is minus 1/2. You add 1 to that, and you get positive 1/2. So there's 2 states that the electron can be in. Well, okay, I guess we knew that already. Let's take 2 electrons, which is really what we're focusing on in this video, is 2 electrons. So let's take the spin number of 1. Now you might say, spin number 1, why is it 1? This line down here kind of tells us what's going on. If we could figure this one out and then apply it to the rule, then spin 1 would be we start with minus 1, then we'd have a 0, and then we'd have a 1. So there are 3 separate states. And if we start with 0, well, there's no place to go. You're 0. Because you're already at this, there is no negative 0 or positive 0. So those are the 4 unique states for 2 electrons. And if you think about it, 2 electrons, all the different spin configurations, that will give you 4 different states. Now, this has yet to be described, but I'll tell you what, this tensor product, and the tensor product involves matrices. So I struggled with this. How could this be, or what is the sense of this relationship? Where does it come from? We're going to have to do some matrix stuff, which actually I like, you might not. But anyway, I'm going to go ahead with that now. I added a very important thing up here. The S bold is an operator valued vector. It's not something that's pointing in space or anything like that. This still is an operator, but it includes all 3 components, X, Y, and Z. That's why it kind of acts like an operator. Now let's get busy now. Busy. Here are the possible spin configurations. Now this part seems easy. Okay, there's 4 possibilities for 2 electrons. They both can be up, or let's say aligned. One can be aligned with Z, one can be in the opposite alignment, or spin 1 can be not aligned, and spin 2 can be aligned, or neither one of them is aligned. So those are the 4 combinations. Now you might kind of compare them with these up there. It's not obvious what's going on there. So we need to, that's what this derivation is all about. So, here we go. S bar squared. Okay? That equals S1 plus S2 squared. Notice we're doing some vector addition here, so that should be important. Now let's go over here and say this expand this out to S bar plus S1, S1 bar plus S2 bar dot product with the same thing. In other words, we're just squaring it. So let's see what happens there. Well, we get an S1 squared. Now notice the bar isn't on that anymore. Then we get an S2 squared plus 2 times S1 bar S2 bar. Before I go to the next line, I'm going to figure out what this S1 squared is. Okay, S1 squared is the X component plus the Y component plus the Z component, and each one of those is squared. Now I'm going to do something you might not like. I'm going to come down here and say 1/2 H bar. So if we square plus or minus 1/2 H bar, we're going to get 1/4 H bar squared, 1/4 H bar squared, 1/4 H bar squared, and that's going to give me 3/4 H bar squared. And then I've got the identity matrix. We'll kind of delay breaking out the identity matrix for a little bit later. Now I want to expand these 2 things. So I'm going to say that that's the X components, the Y components, and the Z components of the 2 electrons. All right, now any one of these SI bars can equal H bar over 2 times the Pauli matrix. If you're like me, you forgot all about what the Pauli matrix is and what it's got to do with spin operators. Here's each of the operators. Each one of these is the Pauli matrix. And look what's out in front of it, h bar over 2. So this should tie some of this in with what we've been talking about. So if I take the dot product of these two, then what I do is I multiply the matrices for each of the different components together. And this h bar over 2 becomes h bar squared over 4. And now what I'm going to do is take all of this stuff and plug it in over on this equation over here. So this was the S1 squared plus S2 squared. So there's a little mistake here in that I didn't have the I on this one, but all of this comes down. If you add 3/4 and 3/4, you get 3/2. So that gives you h squared I. And then if you add these two things together, you pull all this stuff down here. If you take the dot product of both of these, then that's going to give you, multiply it times 2, that gives you h bar squared over 2, and then you've got those matrices multiplied together. Now, before we go on, I'm going to have to come up with another page because multiplying these matrices takes up a lot of space, but it's a lot of fun. Even if you don't believe me, I'm going to go ahead and do it. Okay, I promised you matrices, and here they are. Let's start up in this direction with, this is where we left off from the last page. And what we're going to do now is work on what's inside here. For each one of these pairs of, there's a little sigma for the Pauli matrix. For each one of these Pauli matrices, so we're really just doing the same thing, but expanding it out to 4 dimensions rather than 2 dimensions. Here's the Pauli matrix for X. Here's the Pauli matrix for Y, and the Pauli matrix for Z. If we take the tensor product of these two, this is what happens. I take an element of the first one and multiply it by the whole matrix. See, here's a matrix X, 1 times the matrix X, 1 times the matrix X, and 0 times the matrix X. Well, let's do the zeros first because that makes it fairly simple. If you look at the 0 here, that means I'm going to have 4 zeros in a little cube, and there they are. And down here, I'm going to have 4 zeros in a little cube, and there they are. And I'm going to have 1 times every one of these things here. So it's 1 times 0 times 1 times 1 times 0. And the same thing down here, 1 times 0 times 1 times 1 times 0. So here is the matrix for this one tensor product together. Now that should look a little similar. This one's kind of got an inverse, this one's kind of got an inverse. So that one's fairly simple. Now let's take this one where we've got some i's involved there. Well, let's see. We're going to take 0 times all 4 of these things. So that's going to be 4 zeros. 0 times this 4. So that's going to be 4 zeros. Now in here, I take a negative I times 0 times negative I, and that gives me negative 1. And if I take a negative I times I, then that's going to give me a positive 1, because negative times a negative 1, when those two things are multiplied together. And the same thing happens here. Here's the z result. So all of these things are going to be added together. And if you want to freeze frame and figure out how to add them together, you can. But this is what happens when I add all of these three things together. Get a 1, 0, 0, 0, 0, minus 1/2, 2, 2, minus 1, and a 1 there. So what happens? I plug this thing back into this S equation. So these parentheses are all of this stuff. And I've got this h bar squared over 2 in front and this mess. And the identity operator that I mentioned I would show up earlier, a 4-dimensional identity operator, and it's got a nice diagonal of 1s down this way. That's what the identity operator looks like. If I multiply these constants times these numbers, then I can add these two matrices, and let's see what happens. Well, this one is going to be 3 halves, plus 1/2. See, there's that 1/2. So 3 halves plus 1/2, that gives me a 2. And let's see, 3 halves here plus minus 1/2 gives me a 1. And I keep going along, and this is the result I get. Now, everything would be just nice and clean if I had a nice diagonal here, because that would mean that for every one of these h bar squared values, I'd have a nice result out here. But that's not the case. Here's the problem area, and I'll circle that. Here's the problem area. So what this shows us is that something is wrong with our matrix in terms of coming up with observables. We did all the matrix arithmetic correctly, but there's something wrong with the observable. So that's what we need to fix. Okay, don't be scared. I'm going to present all this matrix stuff for you, just so I can prove it to myself. So I doubt if many people will make it to the end. Please comment if you do make it to the end. But here's the matrix that we came up with our original calculations. Here's a couple of matrices that's going to help us out. This first one builds symmetric, anti-symmetric combinations. But before we can do that, we have to extract the combinations, and that's what this one does. And you can kind of see what's going on, but let's just go ahead and crank it out. Here's the transpose part, and honestly, I'll just give you a few of them. To get this element, I have to take row 1 and column 1, multiply them together and add the elements. So you've got a 2 and everything else is zeros. So that comes up with a 2. Then we take this and multiply times row 2. And that's all zeros. Everything matches up with zeros. Same thing here, matches up with zeros, and this one matches up with zeros. So we got all zeros there other than just the 2. Okay, this one's going to be row 2, column 1, row 2, column 1 is 0. And this one's going to be row 2, column 2. So you take row 2, column 2. Okay, that gives us 1 over square root of 2 twice. So I've got 2 over square root of 2. And row 2, row 2, column 3, that gives me 2 over square root of 2. If you can follow along and do this, you're going to be great at linear algebra. So I'm going to suggest for the rest of this, just freeze the frame and walk through these results yourself. If you can't figure it out, comment, and I'll try to help you through all this matrix stuff.